Hello everyone. So in this presentation, we will be learning about one mathematician, Fibonacci, and some of his contributions towards mathematics. Beginning with the mathematician himself, Leonardo Pisano Fibonacci, most commonly known as just Fibonacci, was a medieval Italian mathematician who wrote numerous mathematical texts that contributed to the extension of mathematical concepts of other well-known mathematicians like Euclid, and he also contributed to the creation of new contributions in mathematics. Fibonacci is most famous for his Fibonacci sequence and the incredible patterns that begin to evolve. The numbers of the Fibonacci sequence are manifested through numerous applications in mathematics, and a couple of these applications will be shown later on in this presentation. We are going to first start by talking about 4 different mathematical texts that Fibonacci wrote, and I will explain each of these pictures after because each one of these pictures represents one of the 4 books. The first mathematical text by Fibonacci is called Liber Abaci, and this is known as the Book of Calculation. This is Fibonacci's most recognized work. In this work, Fibonacci revolved mathematics around arithmetic and algebra that he learned throughout his travels. This book is divided into a few different sections. So in the first section, Fibonacci introduces the Indo-Arabic place value decimal system, as well as the use of Arabic numerals in Europe. The second section of the book deals with problems that were rounded towards merchants, like relating the price of goods, calculating profit transactions, and converting between the various currencies. The final section of this book is where Fibonacci numbers and the Fibonacci sequence was born. Within this section, Fibonacci talks about problems involving perfect numbers, the Chinese remainder theorem, and even problems dealing with arithmetic and geometric sequences. So looking at the top left-hand picture, this is actually a page of Fibonacci's book, and these are just hand gestures that were used to teach people how to count back in the day. Fibonacci's second mathematical text is called Practica Geometria, and this is known as the practice of geometry. In this text, Fibonacci provides a variety of geometry problems and theorems based on Euclid's books, Elements, and On Divisions. In addition, Fibonacci also provides calculations of geometric objects. So in the top right-hand corner, this is actually a picture I found online, and this is one that was drawn using geometric shapes. And if you look closely, it also provides a spiral, and you will see with Fibonacci numbers that spirals in nature are very common with Fibonacci sequences. The third book by Fibonacci is called Flos, and this is known as the flower. Fibonacci considers indeterminate problems reminiscent of Diophantus and analyzes problems with methods employed by Euclid. So for this book, I decided to represent the flower, which is in the bottom left-hand corner, and this is because the Fibonacci numbers are manifested through nature, and it's very common with the spirals and the flowers. The fourth book from Fibonacci is called Liber Quadratorium, and this is known as the Book of Square Numbers. This is Fibonacci's most remarkable work that examines methods used to find the Pythagorean triples and how to construct square numbers using the sum of odd numbers as well. So in the bottom right-hand corner, I just represented this with equations that are squared. Now we're going to dig into the Fibonacci sequence itself. So as you can see, the Fibonacci sequence is 1, 1, 2, 3, 5, 8, and so on. And this can be recursively defined as a sequence of natural numbers, f sub 1, f sub 2, all the way to f sub n, such that f sub 1 equals 1 and f sub 2 equals 1. And for each natural number n, f sub n plus 2 equals f sub n plus 1 plus f sub n. In simpler terms, this means the Fibonacci sequence is generated by adding the 2 previous terms together. And this is actually shown in the middle part of this slide where we see that the 2 numbers added together produce the next number in the sequence. Although we can generate the Fibonacci sequence by adding the 2 previous terms together, the Fibonacci numbers are closed under Benier's formula where we can generate any nth term in the sequence. So instead of adding every 2 consecutive numbers together, we can just find one number in particular and plug it into this formula, and that will produce the Fibonacci number. And this is especially useful when we're trying to find a bigger Fibonacci number. As mentioned previously, I said there were numerous patterns that we'd be able to see within the Fibonacci sequence, and this is where we're going to start talking about that. So we're first just going to look at the top picture. So we see that the multiples are created in this picture. By this, when n equals 3, our Fibonacci number, which is represented by x sub n, equals 2. When n equals 6, x sub n equals 8. From here we conclude that every third Fibonacci number is going to be a multiple of 2. Likewise, when n equals 4, x sub n equals 3, and when n equals 8, x sub n equals 21. Hence, every fourth Fibonacci number is a multiple of 3. And as you go down the line, you will see that the Fibonacci numbers do create different multiples. Now, if we look at the bottom picture, we observe that the Fibonacci sequence creates a palindrome, meaning that the sequence reads the same backwards as it does forward. However, we do have alternating negative signs when we go for Fibonacci numbers below 0. And this part of the sequence can be generated with the equation below. Looking at a wider range of the Fibonacci numbers, one last pattern we can observe is that the Fibonacci sequence goes odd, odd, even, meaning that the numbers in the sequence go odd number, even number. And this is actually one of Fibonacci's theorems, which will be shown in the proof on the next slide. So the theorem for this is for any positive integer m, f sub 3m minus 2 and f sub 3m minus 1 are odd, and f sub 3m are even. We know the Fibonacci sequence is defined as f sub 1 equals 1, f sub 2 equals 1, and f sub n plus 1 equals f sub n plus f sub n minus 1, and that f sub 3 equals f sub 2 plus f sub 1, which equals 2. We observe that the Fibonacci sequence follows the pattern odd, odd, even, and this pattern continually repeats. In general, any natural number is of the form 3m minus 2, 3m minus 1, and 3m. And this proof shows it in general for each m in the natural numbers. We see that f sub 3m minus 2 and f sub 3m minus 1 are odd, and f sub 3m is even. This proof is done by mathematical induction using the definition of Fibonacci numbers. So just looking at the induction step, we are trying to prove that this statement is true for k plus 1. When proving this step, we see that f sub 3k plus 1, f sub 3k plus 2, and f sub 3k plus 3 can be broken down by using the definition of the Fibonacci sequence to generate a sum to determine the specified number. From here we can see in the proof that the three numbers f sub 3k plus 1, f sub 3k plus 2, and f sub 3k plus 3 are in the form of odd, odd, even, which proves the pattern in general. Moving along from all the patterns seen within Fibonacci numbers and the sequence, we're going to talk about two different applications that are applied using the Fibonacci sequence. And this is finding the greatest common divisor between any two Fibonacci numbers using the Euclidean algorithm, and also converting numbers using the Fibonacci sequence. So starting with the greatest common divisor of two Fibonacci numbers, we will see that the greatest common divisor between any two Fibonacci numbers results in another Fibonacci number. We can find the GCD between any two Fibonacci numbers, either consecutive numbers or not. In the example below, we have to find the GCD of f sub 9 and f sub 10, more commonly seen as the GCD of 34 and 55. We observe that by applying the Euclidean algorithm, the last non-zero remainder is 1. Looking at the remainders in general from bottom to top on this slide, you can actually see that the Fibonacci sequence is produced from going from the bottom to the top. In addition, another unique application to apply using the Fibonacci numbers is the conversion from miles to kilometers. We can take any Fibonacci number and multiply it by the conversion factor for miles to kilometers, which is 1.609. The result produces a decimal, and we round this decimal up to the nearest next whole number. Doing this gives a solution that is also another Fibonacci number. So the reason this mathematical application works is due to the fact that Fibonacci numbers tend to the golden ratio, 1.618, as the numbers increase. Notice that our conversion factor is 1.609, which tends to the golden ratio as well. The nth Fibonacci number in miles ends up generating the n plus 1th Fibonacci number in kilometers. So overall, Fibonacci was a well-known and very notable mathematician. He wrote numerous books that all brought about new mathematical concepts and ideas that even tied into number theory and concepts from Euclid. He was famous for his Fibonacci numbers and sequence that holds many unique properties and patterns, and we can apply the numbers to numerous applications.